Good day, everyone. So we're reviewing Wetzel's Limnology textbook. This is edition number 4. We're on chapter 13, the inorganic carbon complex, and more specifically today we're looking at vertical distribution of dissolved inorganic carbon. So let's get started where we left it at yesterday, which is right here. As the intensity of decomposition increases in a tropholithic zone, the amount of CO2 and especially of bicarbonate increases markedly. The accumulation of the sum of CO2 plus bicarbonate exceeds the supply of oxygen, and decomposition shifts from aerobic to anaerobic as the hypolimnion become anoxics. At equilibrium during spring mixes, cold water has about 300 to 400 micromole of oxygen, depending on temperature and altitude. Thus, only about 300 to 400 micromoles of DIC can be produced from the complete utilization of this CO2, of this O2, oxygen. In aerobic respiration in the hypolimnion, which has no new source of oxygen, increases in DIC beyond this amount are due to either anaerobic respiration or fermentation in both the water column and the sediments. Some of these processes also affect alkalinity. If aerobic respiration is the key decomposition process, measuring carbon dioxide over depth will give an accurate picture of the balance between photosynthesis and respiration in the hypolimnion. However, once the system is anoxic, total DIC is needed because of the ANC generated during many of the key anaerobic respiratory processes. In extremely hot water lakes that are also eutrophic, there are additional processes that increase bicarbonates. For example, part of the calcium carbonate sedimenting from the epilimnion, whiting events, undergoes dissolution in the colder, more acidic hypolimnion, resulting in increases in bicarbonate concentrations that are larger than the respiratory increase in CO2. These same events can also strip the euphotic zone of some of its DIC, causing declines in the DIC curve and have been called epilimnetic decalcification. Further, ion exchange with the sediments can also influence the alkalinity. The DIC profile in a lake can show some bumps or wiggles rather than a simple monotonic increase over depth. Where photosynthesis activity in a layer is particularly intense, as might occur in the metalimnion, you might observe a local oxygen maximum associated with DIC minimum. On the other hand, many lakes have a local oxygen maximum that is caused largely by physical, for example, heating and cooling or mixing, rather than biological processes, so no CO2 minimum would be expected. The opposite situation, that is a DIC maximum or a negative heterograde oxygen curve with concomitant DIC and pH curves, is occasionally found in strata of intensive respiration. In regions where the soils and rock deposits contain high carbonates, such as limestone bedrocks, acidified precipitation can increase rates of carbonate weathering and result in increased alkalinity and equilibrium pH in saltwater seepage lakes. In drainage basins and waters with little buffering capacity, however, acid deposition has resulted in the loss of acid neutralizing capacity, alkalinity, decreased pH, increases in sulfate and in dissolved aluminum concentration, and marked alteration in ionic speciation and ratios. These acidification changes can persist on a long-term basis or in less affected areas. Chemical changes occur reversibly for short-term periods. In many saltwater streams and lakes, for example, melting of acidic snow accumulation can result in rapid, a few days, precipitous declines in pH and alkalinity, referred to as spring shock. Lower pH values occurring during late winters and early spring in saltwater seepage lakes, on the other hand, were attributed to increases in partial pressure of carbon dioxide under the ice because total alkalinity did not change at that time. Extremely high CO2 and exploding lakes. Under certain conditions of lake basin morphometry, underlying volcanism and lack of frequent deep mixing, as in certain deep African rift lakes, CO2 and CH4, or methane, can accumulate to extraordinarily high concentrations. Decompression of CO2 saturated water can, with changes in seasonal stabilities of stratification in the upper waters, erupt to the surface at explosive rates, range between 50 to 90 meters per second. So much CO2 is released by this exsolution and evasion to the atmosphere that the dense CO2 over the lake surface can temporarily cascade over the surrounding terrain. Such massive evasions occurred in Lake Nyos and Lake Munon in Cameroon, and over 1,700 humans and many terrestrial animals died due to asphyxiation. There were no measurements of the hypolimnetic gas concentration in these lakes prior to these eruptions. Following the eruptions, gas concentration built up quickly so that by 2004, the deep water CO2 concentration was greater than 150,000 micromoles per liter in Lake Monoun and more than 350,000 micromoles per liter in Lake Nyos. These concentrations are the equivalent of more than 6 atmospheres in Monoun and more than 12 atmospheres of CO2 in Nyos, and were probably even higher prior to the eruptions. For example, for scale, the atmosphere has a partial pressure of CO2 of about 400 microatmosphere or 0.04 atmosphere, so the partial pressure of CO2 at depth in these lakes exceeded the total gas pressure on land by more than 100 to 300 fold. Based on the carbon-14 age of the CO2, most of it has to be of volcanic origin. Limnologists and engineers came up with a practical and relatively inexpensive method to relieve lakes of extreme hypolimnetic CO2 gas. They put open pipes from the surface of the lake into the hypolimnion. The gas pressure in the hypolimnion caused these pipes to act as gas fountains and thereby prevent further large buildup of CO2. So let's look at these gas fountains here on figure 13-7. So gas release vents in Lake Nyos, Cameroon. Lake Nyos built up enormous concentration of CO2 gas in its deep hypolimnion. Most of this gas is from the tectonic activity below the lake sediment. After the catastrophic outgassing of CO2 from this lake in 1986, limnologists and engineers worked toward a simple and inexpensive solution. The gas fountains in the picture are the tops of long pipes that extend into the hypolimnion. The huge partial pressure of CO2 in the hypolimnion drives the release of gas and water from the pipes. Hypolimnetic carbon dioxide accumulation in relation to lake metabolism. While hypolimnetic metabolism is often estimated by the rate of oxygen depletion, it can also be derived from the accumulation of CO2 or DIC. Being based on carbon hypolimnetic, DIC accumulation is a more fundamental metric of organic matter metabolism than the removal of the main respiratory terminal electron acceptor, namely oxygen. In principle, the two approaches should yield similar estimates in systems where the degradation of organic material is largely aerobic and the accumulated end product will stay in the form of CO2. Although often treated as a single ecosystem attribute, hypolimnetic metabolism is really the sum of the two decomposition processes, one occurring in the water column and the other in the sediment. Both processes are positively linked to the overall productivity of the system and the relative contribution of the water column. And bathing processes depends on the main sources of organic matter fueling the catalytic metabolism as well as on the bathymetric shape of lakes. For example, while autonomously produced organic matter, for example, algae and microphyte photosynthesis, sustain most of the hypolimnetic respiration in eutrophic conditions, dissolved organic matter of terrestrial origin can also be an abundant and important substrate, contributing to water column respiration. In deep stratified lakes, most of the respiration occurs in the water column. In shallower systems with thinner hypolimnia or in systems that were Formerly eutrophic, a significant fraction of the hypolimnetic metabolism is benthic. In the benthic environment, the transport of dissolved substances within the sediment matrix is largely constrained by molecular diffusion, with the consequences that conditions quickly become anoxic, usually within a few millimeters of the sediment-water interface, even if the overlying water is fully oxygenated. Thus, depending on the rate at which new particulate organic matter settles at the sediment surface, sedimentary organic carbon can be exposed to oxygen for as little as a few days or weeks, after which decomposition proceeds largely anaerobically, that is, without immediately consuming oxygen. Therein lies the significant advantage of using the rate of DIC accumulation over oxygen depletion as a measure of hypolimnetic metabolism. It encompasses the end product of several respiratory processes, both aerobic and anaerobic. Nevertheless, if the reduced substances that are released to the water column are later exposed to oxygen within the hypolimnion volume, they can be oxidized, ultimately consuming hypolimnetic oxygen. First introduced by Rutner and further developed by Oley, the rate of DIC accumulation was originally conceived as an indirect way of measuring the intensity of the whole lake metabolism. Today, it is more appropriate, viewed as a component of the lake ecosystem that is dominated by respiratory processes. Estimated using sequential profiles of DIC over the stratified period, together with the hypsography of the lake, DIC accumulation rates offer an integrative metric of whole hypolimnion respiration and how it varies through time. Even the exact shape of the DIC or CO2 profile is informative. The observation that the rate of increase in CO2 concentration is faster at greater depth is a reflection of how the sediment area per unit volume of a hypolimnetic layer increases with depth, thereby increasing the relative contribution of sediment respiration at that depth. Livingston and Imboden have used this property to introduce a simple method to estimate the relative contribution of the water column and sediment respiration processes to whole hypolimnetic metabolism. Applied to the CO2 profiles, illustrated in figure 13-6, the method yields an average sediment respiration rate, JA, of 13 millimoles of carbon per meter square per day, and a water column respiration rate of JV of 0.2 millimole per meter cube per day. Note the different units for the area respiration and the volume respiration. Total hypolimnion respiration can then be estimated at JA by the area of the sediment plus the JV by the volume of the hypolimnion. In temperate regions, the CO2 accumulated in the hypolimnion during the stratified period will quickly mix to the surface during autumn turnover, creating a large emission pulse of CO2 to the atmosphere. During the ice-covered period of the winter, a similar process operates with CO2 accumulating under the ice and suddenly released after ice breakup. In many lakes, these two short-lived emission pulses, a few weeks at most, account for a significant fraction of the total annual CO2 flux to the atmosphere and are therefore important to consider when quantifying the annual carbon budget of a lake. In deep lakes, these pulses can account for the majority of the annual CO2 efflux. Utilization of carbon by photoautotrophs and chemolithotrophs. Photoautotrophy and chemolithotrophy. Photoautotrophy and chemolithotrophy. A truly autotrophic organism, in theory, gets all of its carbon from inorganic carbon and none of its energy from the oxidation of organic carbon. If the sole source of energy is sunlight, we call the organism a photoautotroph. If the sole source of energy is from the oxidation of chemical compounds like hydrogen sulfide, we call the organism a chemoautotroph or a chemolithotroph. These are useful distinctions, but in the world of algae and bacteria, there are many cases of organisms that are mixtures of these classifications. For example, both Euglena and Utricularia and many other algae are both photosynthetic and predaceous. That is, they are capable of eating small organisms such as bacteria, and in the case of Utricularia, small zooplankton. Numerous species of phytoplankton are both photosynthetic and osmotrophic. That is, these photosynthetic algae can utilize some dissolved organic matter. We can divide photoautotrophs into two main categories: those that produce oxygen during photosynthesis, oxygenetic photosynthesis, and those that do not, anoxygenic photosynthesis. Oxygenic photosynthesis is the type observed in most aerobic phytoplankton, periphyton, and macrophytes. So let's look at table 13-3 here. So we have some of the key pathways of the photoautotrophic and chemoautotrophic uptake of CO2 in inland waters. So first we have the process, the equations, the kinds of organism, and the change in ANC, which is the acid neutralizing capacity. So oxygenetic photosynthesis, we have CO2 plus water is equal to CH2O plus oxygen, and algae, macrophytes, emergent plants, etc., no change. Anoxygenic photosynthesis, we have 2 CO2 with hydrogen sulfide plus 2 waters is equal to 2 CH2O plus sulfuric acid. Purple and green sulfur bacteria, chromacium and chlorobium can do this. And the net effect on ANC, it lowers it. Chemolithotrophy. So we have 2 types. We have the sulfide oxidizers, where we have the equation of CO2 plus hydrogen sulfide plus oxygen is equal to CH2O plus sulfuric acid. And the type of organisms that do that are thiobacillus, and the effect on ANC, it lowers it. We have nitrification, which is CO2 plus ammonium plus oxygen is equal to CH2O plus nitric acid, shown unbalanced for simplicity. And then we have Nitrobacter, Nitrosonomas in sequence, many other genera, and also that lowers the ANC. And then we have hydrogenotrophic, so carbon dioxide plus 4 hydrogen is equal to methane plus 2 waters. Methanobacterium, and then does both types of methanogenesis, and there's no change on the ANC. And this is the last process we looked at, was methanogenesis. So let's look at this anoxygenic photosynthesis. So anoxygenic photosynthesizers include the purple and green photosynthetic bacteria. These organisms are photosynthetic, but instead of oxidizing water to hydrogen and oxygen, they oxidize other reduced species, including sulfur compounds, purple and green sulfur bacteria, and other reduced compounds such as hydrogen, purple and green non-sulfur bacteria, because these anoxygenic bacteria require both light and a source of reduced compounds like sulfide. They tend to exist in narrow layers in lakes where both light and sulfide are available and where oxygen is low or absent, so near or in the anoxic zone. They can also occur in hot springs where there is a geothermal source of sulfide and abundant light. There are also both purple and green non-sulfur bacteria. These groups are non-taxonomic units. The term non-sulfur was used because it was thought that these organisms could not use sulfide. Many of these bacteria, especially the green and purple non-sulfur bacteria, are photoheterotrophs, subsidizing anoxygenic photosynthesis with the heterotrophic uptake of some carbon compound. Okay, so we'll be ending up today with the vertical distribution of inorganic carbon in lakes, and as well as looking at organisms that are responsible for the use of this dissolved inorganic carbon in lakes and rivers. And I'll see you tomorrow. Bye.